So you have your efficiency scores. You have the scores for each group. You have the scores for each variables. And these scores are very, very, very important. Now, you will have the scores across firms. You have the efficiency or productivity scores. You have the efficiency and the productivity scores across time periods. You have them across firms. Some of you do that. You have them across time periods. And if you're using MEA, you will have them across individual variable specifics. You may even have them, the efficiency scores, across different methods. So, or different approaches. So you may have them across CRS, constant retention scale. You may have the scores across VRS. Okay, so across different methods. So across methodologies, across different categories of groups of firms, across different time periods, across variable specifics, and other aspects. You have the scores. How do you explain differences in these estimated, across the score? So let's say that you have them. How do you explain that the foreign companies with these scores, okay, based on the scores, are outperforming the domestic companies based on also their scores? How do you do that? How do you say that these scores using the CRS outperform the scores using the VRS? How do you do that? How do you use the scores to determine that the productivity, okay, coming from efficiency change productivity, contribute more to productivity, significantly speaking, than that of efficiency coming from, say, technological change? How do you explain the differences? Knowing how these factors or these drivers, okay, of efficiency and productivity gains, knowing them can affect the performance is a critical aspect of determining the performance of it, because then you can now make an improvement and you can now evaluate the cost of government regulations. This is what is known as the second stage regression analysis in DEA, data envelopment estimations. Now, in order to best explain this, we need to understand some few things about a statistical model. I'm picking most of my points from Casals and from Simmer and Wilson. We are going to formalize a statistical model. It's not going to be complex. I'll jump some of them. So if you have a statistical model of a production process, and this production process generates some random variables, X, Y, and Z. Okay, I'm just formalizing. So obviously there will be some mathematics. And you do this in an appropriate probability space. Now let me just give you a fair idea of what I mean. Now let's assume that you have a production space. Like something like that. You have a production space. Something like this. In this production space, you have some inputs that are actually producing some outputs, or the inputs are entering into the production space. Okay, and there is that particular DMU inside the production space, and they will process those inputs, and eventually these inputs are converted into some outputs. Let me make it 4, so that doesn't look like 3 inputs automatically generates 3 outputs. Okay. So you have this. Now, that is what we normally do in a DE efficiency analysis. But there was a factor we did not consider. There was a specific factor that should have been considered but wasn't considered, a Z variable. There are some Z variables that are also affecting the behavior or the performance that we are looking at. Let's call it Z1, Z2, and then Z3. But these were actually not considered during the production process. Okay. Now, with that, let's move on. Now, these vector of variables, these Z variables, we call them environmental factors. You see this in the literature a lot. They are also called uncontrollable factors. Uncontrollable because they were not within the control of the managers. They are outside their managerial control, especially in the agricultural industry, where rainfall is outside your control. Okay. Certain things that are outside your control. Contextual variable is another name. So in a banking industry, you have size. The size is outside the managerial control. They're outside the managerial control. Corporate social responsibility may be outside managerial control, so may be considered as an environmental or explanatory variable in a regression. These are outside of management, so they are also called exogenous or external variables. Some of them are quite invisible, so they become like confounding variables in a regression, which are sometimes called unobserved heterogeneity. You will learn these things. If it is firm specific, like competition, competition is an industry specific. If it is firm specific, like ownership, corporate governance, okay, these are firm specific. Size is firm specific. Size was not captured as an input or output, so it becomes a covariate. Let me put it that way, an environmental variable. So these Z elements, they are neither inputs nor outputs, and they are typically not under managerial control, but they do influence the production process in different ways. And that is why, after analyzing the efficiency scores, after generating these scores, estimates, okay, whether you did a bootstrapping or you didn't do a bootstrapping, and I'm going to say this because some people would think that since I did not do bootstrapping in the first stage is where you estimate efficiency scores. Since I did not do bootstrapping and I got cost productivity scores or Manquist productivity scores, I will not be able to do the second stage. You can do the second stage, okay, because those factors are still going to influence the first stage variables. So you can formalize it and consider something we call the separability. I want to mention that the Z variables that you are having here, you need to be able to establish that these variables are not in any way captured inside the production process when you are converting the inputs to an output. They are not captured. You got to make it clear. You got to know in your mind, okay? But knowing in your mind is not enough. You got to test it. And this is known as the separability condition. The separability condition, I will not bore you so much, but I want you to just know the theoretical underpinning a little bit. It just shows that, okay? I'll tell you about this separability condition, okay? Because the restrictive separability condition, you just have to know it. In general, it says that it should be possible to separate the Z variable, that is those environmental factors, the covariate. It should be possible to separate them. It should be possible to say that they did not truly influence the first stage analysis. They were not captured in the first stage analysis, and that is why you want to capture them in the second stage regression analysis. In other words, there must be a kind of a knowledge and an understanding, a statistical understanding that they were not captured. So it's very useful for the second stage, because the second stage is needed provided you can prove that there was a separation between the input output and the Z variable, which is environmental factors. This was initiated by Simon and Wilson. And what it says is that the strong separability condition says that Z, okay, is possible. Okay, Z only affects the distribution and does not affect the production. Now, this is important. Now, in the production, now, when you go to the chart that I just showed you, and this is quite technical, so you want to pay attention. Okay. Now, this one, the X's and the Y's, they are affecting the production possibilities. The Z's are not affecting the production possibilities, but they affect the distribution of the efficiencies. And that is why you later capture them in the second stage. So Z affect production process only. Well, I remember I told you that they don't affect the production possibilities, but they only affect it through the distribution of the efficiencies or the inefficiencies, which depends on the production process, So in order for you to do the second stage, the separability condition must hold or must be satisfied, else DEA or FDH or MEA, I must say that, MEA, FDH is free disposal hall. Most of you don't use it, but there's something that is very, very nice as well. In fact, certain situations have even proven that this FDH are sometimes nicer than the DEA. So all of these estimators, they become useless if the separability condition doesn't hold. If it is not clear that there is a separation between the Z variable and then the production possibilities. Okay. And so these estimators, once you get the scores become meaningless because the Z may influence the level and the shape of the boundary of the production possibility set. And therefore, if you don't satisfy this separability condition, the second stage regression becomes difficult to interpret. If the Z doesn't affect the attainable set, that is when we say that the separability condition holds. Because I've already told you that it should not affect it, but it should affect the distribution. Okay. Of course, it affects the production possibilities through the distribution of the efficiencies. So in other words, you can only talk about this Z variable only after estimating the efficiency scores. And the process is this. Estimating the efficiency scores is known as the first stage. The first stage. And then regressing these efficiency scores on those Z variables, those environmental factors, is the second stage. So here's the thing. Many studies pursue the two-stage analysis, and the two-stage analysis is defined as efficiency or productivity scores, which are estimated in the first stage, and then simply regressed. Now, are they being regressed? They are being regressed on because they are conditional. They depend on, in some complicated way, they depend on some independent variables. They depend on some environmental variables. They depend on these contextual or exogenous factors that are neither inputs nor outputs in the production process. Okay. And so the second stage is where you bring a regression to look at the connection between the score you've estimated and that of the Z variables that you have, which of course were not captured. And so Diana, you might remember I told you that in your second stage, you may not have captured certain things in the first stage. And so if carbon dioxide emissions was not captured, it should have been captured but wasn't captured in the first stage, then you want to bring it in the second stage to see its impact on the efficiency scores.
Yes, sir.
However, there is a debate regarding which regression model is used, because as it sounds, it clearly shows that there is a regression here. Because regression, the word regress means that there is a regression. And a regression is where you formulate some dependent variable on the left-hand side, and you have an independent or several independent variables on the right-hand side. Now, there is a debate as to which regression model is appropriate for this two-stage. There's a lot of debate. We'll arrive at something very soon. Okay. So first, you compute your year-by-year efficiency scores or the pooled efficiency. Now, year by year efficiency scores means that you consider all the DMUs in 1 year, okay? You don't take another year. You consider all the DMUs in the year 2000. You estimate the scores for each one of them. Then you take all the efficiencies, all the variables in year 2001. Then you estimate the efficiency score for that. Then you take all the variables, both input and output variables in 2002. Then you put it into the system and then you estimate efficiency score. These are year by year efficiency scores. But another thing you can also do is this, and please listen. You can put all the variables in one panel and then run the efficiency score for the entire frontier against the entire frontier. So this becomes a kind of pooled frontier. This becomes a kind of a common frontier because they are all in, all the years doesn't matter here because all the firms, if a firm is in, you can have firm A in year 1 and you have firm A in year 10. They are all being measured relative to a common pooled frontier. That is a pooled efficiency. So the score you will get is known as a pooled efficiency. It depends on which one you go. Now, we've already established this thing in the meta frontier framework, where we said that when you measure all of them against one frontier, which is a pooled frontier, also called a common frontier, also called a meta frontier. If you do that, then the scores are comparable because they are all being measured in the same technology set. But when you do them separately in each year separately, you create a frontier, separate frontiers in each year, then you cannot compare the scores. Okay? Then you can't compare them. You can't even say that this year, 1 firms are doing better than year 2 firms because they are all being measured in different frontiers. So once you estimate their scores or whether it's efficiency, you can also estimate productivity scores and the component. You can estimate that, and then that becomes your first stage scores. Then the third thing is that you will now account for these environmental factors that will influence efficiency. This is the second stage analysis. So guys, when you always hear of the second stage analysis, the first stage is estimating the efficiency or the productivity scores, and the second stage is doing a regression, where these efficiency or the productivity estimates, whether they were bootstrapped or not, are regressed on some covariates in the second stage. Why do we need the second stage? And listen carefully, okay, why we need a second stage. DEA is a wonderful technology. DEA is a wonderful methodology for assessing the performance, the relative efficiency of decision-making units. That's DEA. And it uses multiple inputs and multiple outputs, unlike regression, where you have single inputs. So DEA has a lot of advantages. You can even split the scores into technical efficiency, allocative efficiency. You know, you can have scale efficiency, you can have profit efficiency, revenue efficiency, cost efficiency, and so forth. You can have different, so that you can know the sources of efficiency. So DEA is wonderful. But you see, what it does is that it treats the production process like a black box. In a black box, you have the inputs being transformed in the production process to generate the output without telling us the explicit modeling of how this transformation occurs. What is really behind the scene? What is happening? The input, okay, you dropped in some inputs and you dropped in some output, and all of a sudden something comes, and that's something that comes as a DEA estimate or a score. The process is like something out of the blue. It's like a black box. That's the first thing. So we need to know what is impacting on the scores that we don't see. Secondly, DEA is very sensitive to the presence of outliers. We know that it's an outline methodology. Now, for those of you who are probably fresh and want to understand these things, okay, DEA is something like this. You have some things like that. You have an input and then you have an output. Okay, And then let me just create a DEA frontier. Okay, so this is like a VRS frontier that I've created. You have some inputs, some variables, okay, that are all inside. You have some variables that are on the frontier. They define the frontier. Okay, and you have that. Now here is the thing. The thing being discussed here is that before I created these lines, and let me just show you something. These lines. I was selecting things that were on the edges, You see, a regression line would throw a line. A regression would throw a line along this and then use the mean, and that will minimize the weighted sum, okay, of the errors, and then come out with the scores in a stochastic frontier analysis, okay, making a lot of distributional assumptions and other things. But what the DEA is doing is that DEA is picking the extreme values. So let's assume that there was one particular extreme value on the far left here. DEA will pick that. And if that is an outlier, then that outlier is going to define the efficiencies of the other firms. Okay. So DEA uses these extreme guys, and then we are now, so if each one of these guys is an influential variable, then that, because the others, these other guys are going to, their efficiencies are going to be measured, okay, in the input direction or in the output direction. So if I want to measure this guy's efficiency, I will now move leftward. You see, the frontier is now helping me to, okay, I'll move upward in an output direction. Or even if I want to move a hyperbolic direction, I can move that. Or a directional distance function approach, I can do that. So the thing is that if the frontier is estimated by the extreme observations, then it means that they can affect the efficiency of the other guys. And so DEA becomes an outline method. And you know that outliers are a bit of a problem in a regression. And so that is why we've got to bring this second stage into the picture to address what? To address the issues that are all complicated. And of course, anytime you have an outlier, then you have issues of random noise. And so we deal with that. The other reason why we need the second stage is that the efficiency scores or the productivity scores, which becomes the dependent variable. Listen, please. These dependent variable efficiency scores or the productivity estimate, they are not directly observed. You see, in a regression, you observe the data, don't you? In a regression, you have some data that you observe. Okay? Let me just give you some, and I want you to understand these principles very well because it will help you. So in a regression, you have some Y variables, okay? And then you have the variables all there. Then you have X1 variables, okay? You have all of them, okay? Then you have X2 variables, okay? These are the independent variables, X3 variables, okay? You have all of them showing. You have X4 variables, you have all of them. These variables, they are observed. You can see them. You can see them in an Excel. You can see them in R software. You can see them existing. The variables, you observe them, you collected them. They are in the annual reports of banks or other institutions. But then when you go to DEA, this section here, the scores, which now becomes the efficiency scores here, okay? Whether it's input oriented or output oriented, that score is not directly observed. You don't see it in the annual report of banks or others. You have to go and do what? You have to go and estimate them. They are empirically estimated. And the process of estimating them, they are estimated relative to an unobserved frontier. Remember the frontier, we created them. It wasn't observed itself. That word, unobserved, when you bring it into the world of regression, regression doesn't like things like unobserved. Regression deals with them very critically. That is why the issue about unobserved heterogeneity, unobserved disturbances. And so, because the efficiency scores are not observed, they are estimated relative to an unobserved frontier, it leads to some strong correlations among the scores and some biases in the scores. Now, let me tell you why. Why correlations? Watch the estimation. Watch the estimation here. I told you that this DMU, let's call it DMU A, the score is being measured relative to the frontier. Okay, let's say that's being measured to the frontier at point B. Okay, at point B here. You are measuring A relative to who created B? Okay, B, the frontier, okay, was created by those other firms. So the efficiency of A will be dependent on the firms that are forming the frontier. Okay, the firms on the boundary firms. So it becomes the score of A, the efficiency score of A becomes a relative score. Okay, the efficiency score of A becomes what? It becomes a relative efficiency score. Relative. Why relative? It's relative because the score depends on a frontier. And so also already there's some kind of correlation, because when something is relative, it's a correlation. There's some kind of correlation. Your score that you will get here, it has some correlations with the score of this guy or with the frontier that has been estimated. So there's some correlations there. Okay. And that is a serious thing. Okay. Because those strong correlations has to be dealt with. So the moment you now use efficiency scores as the dependent variable, remember that inside that score are some correlations, and these correlations have not been removed. And so they bias the scores in the first place. The next thing is that the dependent variable, which are going to be used in the second stage regression, we've already indicated that they are unobserved. And because they are unobserved, they have to be replaced by an estimate in the regression. Okay, because they are not observed, you have to replace them. Now, the estimated scores, the dependent variables, which are used in the second stage, they are serially correlated. This is a similar point that I've just made. They are serially correlated in an unknown way. This is according to similar ways. And remember that we mentioned the issue about the separability condition. So due to the separability condition, the inputs and the outputs are correlated with the independent variables that you use in the second stage. Now, remember this. Remember that the inputs and the outputs used in the first stage, listen carefully because this is a little bit technical. The inputs and the outputs in the first stage, those inputs and outputs were the ones that generated what? The efficiency scores. So there's a correlation between the inputs, outputs with the efficiency scores. Now, these efficiency scores are going to be used in a second stage regression. In that second stage regression, they are covariates, they are independent variables. These independent variables were not inside the inputs and outputs. But then the inputs and the outputs are correlated with this independent variable, with the dependent variables, which is efficiency scores. And you need to have some correlation, because before you can do any regression, there must be some correlation between the independent variables and the dependent variables. There must be some correlation between the independent variables and the correlation and the dependent variables for a regression to even be warranted. And so already those independent variables, the covariates, which you said earlier, okay, you said earlier that they are not in any way related to the efficiency scores in the separability condition, because the separability condition must hold. You said that they are not in any way related, and that is why there's a separation. Now, they must be related, because for you to do a regression, they must be, okay, and so that makes the error term correlate with the dependent variables. Now, when the error term is correlated with the dependent variable, one of the assumptions of regression you will see later is independence. There must be zero covariance. Okay. We sometimes say that the expectation of the error term must be zero, but there must also be no heteroscedasticity. Heteroscedasticity. Okay. So the variance of the error term must not show some pattern, it must show some constancy. Okay. But then there must be independence no correlation between the error term and then the independent variables. Now, right now, looking at the way things are, there's a lot of correlations. That is why Simon and Wilson says this is so much correlation in a very complicated way. So the error term becomes correlated with the covariates, the independent variables, which are not accounted for in the first stage estimations. These are the reasons why we got to do the second stage and do a proper second stage. Again, a proper second stage. Now, finally, on this point, efficiency scores are normally between 0 and 1 in an input orientation. Okay, and they are actually 1 and above in an output orientation. So we know this. We know that 0, okay, the input-oriented efficiency score is between 0 and 1, like that. The output-oriented efficiency score is 1, okay, and above, and 1 all the way up to infinity. Now, you can see that most of the time, okay, the efficiency scores that are firms that are efficient will carry a score of 1. And so usually, not all the time, but usually, there is a higher mass of probability of the scores at 1. Majority of the scores, or most of the scores are 1. Okay. Now, we would have expected some normally distributed kind of thing, but then the scores are 1. So most of the scores peak at 1. And we know the efficiency scores in an input-oriented is limited between 0 and 1 interval. Of course, the output-oriented can be, you can take the reciprocal and also bring it to between 0 and 1. You can do that. And so that situation where the scores are restricted, okay, it should be accounted for in the second stage. Okay? Because those, how do you deal with efficiency scores? Because those scores now make the whole thing skewed. And if it is skewed, then is regression going to do a proper job? What kind of regression? What kind of, is it OLS that's going to do the job? Or it's a different kind of regression that's going to, okay. So that whole thing has to be handled. And that is the reason why we got to also address the second stage. So ladies and gentlemen, the second stage, you got to motivate your second stage. That's the point. You got to motivate your second. And these are some of the studies that have actually done second stage regression. Some of them have done it, second stage regressions, and they've done their measures in MAMQuest, using MAMQuest productivity. And some have done second stage using efficiency, technical efficiency. Some of them have done cost efficiency and all of that. So I've given you a few of them in the countries some of them belong to. Right now, for those that have done cost productivity, the only second stage paper that I know of is my own and Charles's. So we have done a second stage regression, okay? And we have mooted this idea of the second stage. However, the second stage, I've told you that it's a little bit complicated. So you want to be able to. So at this stage, we want to now pursue the second stage regression. It's a regression, and so you need to know something about econometrics. Yes, if you are able to do bootstrapping in the first stage of efficiency, that will take care of the extreme values problem, because the extreme values will come with these biases. Sampling variations will be handled, generally speaking. And then you can also handle some of the correlations. That correlation between the DMU's efficiency scores and the frontier, all of those biases can be handled using what? Bootstrapping. Now, so when you bootstrap the efficiency or the productivity scores and you bring it into the second stage as a dependent variable, that score presumably has been dealt with bootstrapping, so it's sorted. However, you're going to regress that score on some environmental factors in the second stage, which is like any normal regression, which of course comes with its own what? Assumptions and its issues. For example, assumptions of linearity, assumptions of homoscedasticity, assumptions of no autocorrelation, assumptions of no perfect multicollinearity. We'll look at these things, don't worry. Assumptions of, strict exogeneity or weak exogeneity, okay? Assumptions of autocorrelation has to do with the two errors, but then you can have what is known as independence, which is between the errors and then the independent variable. Okay? So there must be no independence between the errors and the, because that will lead to what is known as endogeneity. See? So there mustn't be those issues related to endogeneity and all of that. And then there must be no misspecification biases and other things. These assumptions have to be dealt with again, even in the regression. And therefore, you have to again correct for this. And more even importantly is that, unlike regression, okay, you said that the second stage variables were separable from the input and output you use to estimate those scores. And so we have an added problem of serial correlations because they might not, they may not be necessarily separable. Okay? And that is why we need a double bootstrapping of the scores to be able to come out with, every situations that we have there. So that warrants a lot of regressions in this. And this is one of the main reasons why the second stage has become a very big topical issue. To do the second stage, I want to just let you understand some few things about regression. And before you can understand something about regression, you just need to understand something about correlation. Correlations. Correlation is a relationship between two variables. They're called bivariate correlations. It can be strong or weak. It can be negative or positive. If it is negative and it's getting closer to -1, then it is high negative. If it is getting closer to +1, it's high positive. But we normally focus on the absolute value of the results to indicate whether it's strong or weak. There are various measures of correlation, Pearson's, Spearman's, Kendall, and other things. Okay. Pearson's is a parametric one, and the rest are non-parametric. And when you are in your second stage regression, you'll be using the Pearson's correlation to get a correlation of all the variables. So this is like a regression. You have dependent variables, independent variables. You now do a complete correlation analysis. But before you do that, you have to do some things. You have to do some things before you do the correlation. And in order to best understand that, I'm going to teach you how to go about this. Before you do the correlation, you have to do something we call descriptive analysis and contingency analysis, depending on whatever. And then you do the correlation. You now do the isotonicity tests. You do the correlation, you do the isotonicity test, and check for potential multicollinearity and other things, okay, which we shall get to. The best way to teach you this is by taking an example. So I'm just going to take an example and walk you briefly through how you can address this. By taking a completely different example, not an example related to DEA efficiency scores, because we'll look at that example later. But I want you to understand certain basics of regression first, okay, before you can now appreciate that. So I have decided to collect some data. This data is called Brukutu Venture. Some of you may have seen it before. It's a local gin distillery that is concerned about the demand for its gin bitters. Most of its retail shop has been hit because of the new entrant. So management want to know which predictors aside the price, can affect. Price is one of the factors that can affect the quantity demanded. But there are other factors that can affect demand. What are those factors that can affect demand? Some of them include the complement price, the average real income of customers. This is the data. So you have the quantity demanded. This is a cross-sectional data. It's just 1 year, more or less, data. We don't have multiple years. And you have the quantity demanded is dependent on the price. Now, if it was our efficiency and productivity analysis, this scale will become our efficiency scores. And the scores will not be bigger numbers as you see here. They will be between 0 and 1, plenty like that. But like I said, I just want you to understand some basics of regression first. This is a multiple regression because the dependent variable is 1 and the independent regressors are many. P is the price of the product. C is the complement price of the product. N is the income of the people, the average income of the people. All of them have been explained here. And the rest of the variables are dummy variables, where you believe that the location of the shop can affect the demand. So the location of the shop is either urban or rural. Some of you will be having dummy variables like that. Some of you will be having dummy variables, like those of you who are having what? State banks versus private, or domestic private versus foreign private, or Nigerian, foreign Nigerian versus other Nigerian. So some of you have that. Okay. Now at this stage, I'm going to let each one of you tell me what are some of the dummy variables you might have in your own situation. Let's box on. So you have dummy variable like location, which affects the quantity demanded. Occupation of the people, whether they are teaching, fishing, or trading, that can affect their demand for gin bitters. Remember, this is the demand for gin, alcohol, bitters. And then the religion. The religion can also affect. Okay. Which of them do you think they are more likely to demand more alcoholic gin bitters? Which of these religions? Who can tell me? Who can raise a hand and tell me which of these religions is more likely to demand more of alcohol?
Christianity.
Christianity, that's true. That's true. There's no question about that. If you don't agree, ask your Christian pastor. Okay. Ask your Christian pastor. The Christian pastor will sort you out. Okay. So they are very good at some of these things. So these are the variables. Okay. Now, normally you will know the total number of variables by putting it into the system. So this is a variable that we want to work with in the regression. Okay. All right. So what we want to do now is to want to go to the next stage to examine the location. Okay, so the first thing we want to do is to generate some descriptive statistics for this data. And in this context, I've explained all of the dummy variables. And in your work and your thesis, you'll always have to, beautifully explain the dummy variables that are being used there. This data is in Excel, so you can use Excel to quickly generate descriptive statistics. That's an easy way, but you might not get enough, depending on what descriptive statistics you want. Okay. And since we have been stuck to using R, I'll be using more of R. And in some cases, very specific cases, I'll be using the Excel for it. Now, you can put in this command in R, and then you can now ensure that certain packages are involved. I want to just show you one of those packages. Okay.
Yes, please.
This is the data in Excel. What we want to do now with this data is, you can see all of the information content here in the Excel. Have it all there. We are going to now take this data into R and work with it. Okay. Now, let me show you what the R situation is currently. I have all the commands written here already, but let me just zoom in on some of those commands for you. So these are the commands. These are the commands that you have. The first command that we are going to deal with is to load the data using this highlighted information. That is it. You all know how to load data into R. So I'm going to load the data into R. And to do that, I'll just go to my Excel, and then I'll copy. I'll highlight all of the data as you see here, and then I'll copy the data. Once you copy the data, you go to your arrow. Right now, I'm in my arrow. Let me zoom in into my arrow, and then I'll click here, and then I'll run it. I'll run it, boom. Once I run it, I come down here, and you see that you have the whole thing written nicely blue, which means that the data is what? Is loaded. Okay. That is an indication that the data is loaded. Okay. How do I know that the data is loaded? Just go up there and then just highlight only the gene. I labeled it as gene equal to read.delim. This is the way we loaded it. You all know this. And then now you can see that the data is beautifully showing. Just as it was. And the names are there. LOC or location. OCCREL. So your data is beautifully loaded there. There are some packages that can organize the data nicely for you. I'll talk about this at a later time, and I want to do it quickly. You can look at this on yourself. These are some few packages that you can install in R and load. They can usually help you to be able to get some few things. The most critical one is the library stargazer. Okay, which you have to install and then load. So now let me just do that. Now this command loads it, library stargazer. Okay, it actually loads it there. And I've loaded it. It says please cite. Whenever you are using it, you cite this alter. Now I'm going to now do something. So first you load the stargazer and then you do that. And then this command will select the variables that are not dummy variables, the numerical variables. It will put it in a beautiful table. The stargazer simply puts things in a beautiful table for you, like you would have seen it in latex. Okay. So let me see if it is doing that. So it says it has not found this function, which is percentage greater than percentage. So the best is to load all the packages. I didn't want to do that, but then let's load all the packages. Okay. One of them will help you get that. I think it is a tidyverse or the Megrel TT. So I load this thing, and then after installing and loading this, you just do this command, which is gin. Okay. And once you do gin, this is what you see. Okay. This is what you see down here. You see that it has organized it like a table for you. Do you see that? Okay. Beautifully organize it like a table. You have the N, which is a sample size, and you can see that it only selected the numerical variables, the mean, the standard deviation, the minimum, the 25th percentile, the 75th percentile, and then the maximum. That is how it is. Now, this command, which is a summary, will give you the same thing, but not in a beautiful way. Let me just show you. Give you the same thing as you see down here, not in a beautiful way, but it's okay. It's okay. So you can then export this into Excel, and then you can now organize it the way you want. I like the way it gives, because most of the time, the one you need is just the minimum values, the maximum values, then the mean, the standard deviation. But as you can see here, it doesn't give you the standard deviation. Okay. If you are dealing with efficiency scores or productivity scores, you can add the median, okay, for certain purposes, because it's a non-parametric skewed kind of data. But you can see that the numerical values have all been nicely given. But look at the dummy variables. They did not give you the summary statistics of the dummy variables. Watch it. Who can tell me why? Why is it that they did not give you the summary statistics of these dummy variables? Anybody with an idea why that is so? Christopher, why?
Because I think it's because the dummy variables are categorical.
Exactly. And when you are showing a summary statistics for categorical variables, you don't need a mean for gender, male and female, and you tell me what's the mean or the median or what's the minimum of the gender. You can't tell. It doesn't make sense. R is sensible. And so R will not give you that at all. Okay. It tells you about the class and then the character, but sometimes it tells you about the quantity. I don't know why this one did not do that. Okay. But all the same, let's move on and then let's look at some few descriptive statistics. Okay. Everything that you see here, I've already shown you. Now, that summary gene, the name of the data we gave in R is gene. That summary gene, to be honest, it doesn't give us a lot of information. Like I told you, it didn't give us a standard deviation. So if you want more information, you install and load this command called require site. And this require site will help you to be able to now get more by, instead of using summary gene, this time you use describe gene. So let's go do that in our R and see how things will look like in our describe gene. So we do the require and then we do describe gene. And this is the information that, when you look at this information down here, see the describe gene is up there. I run that if I run this. Now look at the beautiful thing. It tells you about the dummy variable. Location, it puts a star there. Occupation, it puts a star there. Religion, it puts a star. Again, R is telling you that even though he's giving you numerical values of this, they don't make a big deal. That's the point. Okay, you should not rely so much on them because these are dummies. So even though he's telling you that the location, the mean is 1.5, you can't have 1.5 of rural and urban. Okay, other than that, they become urban. Okay, and there's nothing that makes sense like that. And so the good thing is that R tells you that don't focus so much on this. But then the others, you now have what? Your mean, you have your standard deviation this time, you have your median, you have your trend mean, you have your minimum absolute deviation, you have the minimum value, the maximum value, the range, the ketosis, the skewness, and the standard error. All of these are given to you. In most journal papers, in most theses, you basically will need the mean, the median, the standard deviation, minimum, maximum. Unless you are really dealing with scores, then you might want to look at a bit related to the skewness or the coefficient of variation. So that is it. You've been able to make the description. You can take this one into Excel and then talk about them. Now, at this stage, if you have location and your focus is on location, okay, you can now describe the information according to location. You can describe the information according to location. Okay? And I will try and see if I can do one for us here. Okay? Just describe some few things about the location. Let me see if I can do describe by location. Let me see, describe by location. Describe a location. Let me put the location into the data set. Location $gen. Okay. It looks like I need to just use a certain approach. Okay. All right. So let's do the describe by. I just want to change my describe by with something like this. Okay. So describe by lock. Describe by lock. Let me just zoom in slightly for you to get the idea what. So I want to describe by. I want to describe the gene by location. Okay, so I use this command, describe by gene in the location. And then you have that. But before I do that, I need to attach the data. I need to attach the data, or unless I use lock $gen. Oh, I didn't use that. Okay. So let me just go back. Invalid closure deprecated, please use describe. Oh, okay. I'm using a different command. It's supposed to be described by capital. And then lock. Let's see if this works. Okay. And now I have to add my $and C. Other than that, I have to attach it. All right, so the best is to do an attachment. I hardly don't want to attach. And always when you do attach, so we want to attach the data called gen. And then don't forget to detach later on, okay, so that it doesn't stay in the memory. So you attach, but don't forget to come and run this detach. After you've done the attach, describe gen by location. Okay, you describe gen by location, enter. And what it does is that it gives you the information according to rural and urban. It gives you the, so sometimes somebody wants to know the mean for the shops according to the rural, then the mean according to the urban. You can describe it by any group. You can remove the location, okay, and then change it by religion. Okay, so you can describe by religion. And when you go down here, you see that it has divided it into Buddhist. So the mean quantity demanded of gen by Buddhist, that is 180. The mean quantity demanded by Christians is 206. Okay, and the mean quantity demanded for Muslims is 147. So it appears as the Muslims are not demanding a lot of that. The Muslims are demanding lesser quantities of what? Gen. So this descriptive statistics helps you to have a feel of how everything is, you know, in that particular regard. And that's a very beautiful way. So describe by will give you the information. So those of you who are doing group analysis, ownership, diversification, all of this, you can now describe your statistics according to group after you've done it for the whole of the information content that you are looking for. Okay. All right. So with that done, let's now go to our information requirement. So this is the described by that we indicated there, and the one by groups is what we have it. Now the next thing is to show a bit of graphs, and I'm now moving away from efficiency and productivity analysis so that you can just appreciate a bit about regression. A bit about regression. You can use this command par inflow so that all the next graphs you want to show will be inside the one graph. It's just be 1, 2, 3, 4, all of them on one. So you can do a lot of graphing. Quick one, you can do a histogram of the quantity demanded. You can color it yellow. You can plot the density for price, is another independent variable. You can do the quantile normal probability plot for quantity. You can do a box plot. So four main graphs, histogram, density, normal probability plot, and box plot. Okay. And the box plot, you can do all of them according to the groups. In this case, the groupings are occupation. So you can do all of that and then represent them in one graph like this. Okay. You can try this and represent them in one graph. And all of them. So the par info, that command I gave there, this par info simply allows you, because sometimes your thesis, you don't want a whole page taking one graph, another whole page taking one graph, another whole page. So sometimes you can have all the graphs. And it makes it beautiful. It makes it easily comparable if you want to compare them. Right? We can even do 3 by 3. Okay? Or we can do 3 by 2. 3 graphs where you have one more here, one more below. Now, the next thing, which is why we came here, is to have the correlation analysis. The correlation analysis. So what I want to do is this. I want to go to the Excel, and this is the Excel. And I want to show you how you can do the correlation analysis. But here is this. It's very important to appreciate this. And you have to do this correlation analysis. You can do it in Excel. You can do it in Excel, you can do it and merge the two, whichever way you want. Okay. Excel has this advantage in this very sense. Okay. Because Excel cannot do this dummy variables. It cannot do, because Excel doesn't see it as numbers. They are not strings. And when you go to R will not even recognize it as R recognizes them as dummy variables, but it will not calculate the correlations for them because they are not numbers. So you got to code them as numbers, and very simple to code them. I have coded them in this next sheet. I've coded them as numbers for you. Okay. Where LU is representing location being urban. So anywhere you see 1 is representing urban. 1 is representing urban. 0 is representing rural. 1 is representing urban, rural, urban. Okay. So you now have this to be urban and all of that. Then when you go to occupation teaching and occupation trading, I did not bring occupation teaching, occupation trading, and then I did not bring occupation fishing because that is a reference category. So in this column, you create that. Now, how do you do that? You can tell Excel to do that for you. A very quick one. Okay. Let me just take religion. Suppose I want to create, I can put it into a new sheet here. I can create a new sheet, and then I can just copy this and then bring it into this religion here. And now I want to create for religion Christian. I want to do, so let's call it RC, religion Christian. So wherever we see Christian here, we should call it 1. Every other thing should be 0. So what do you do? Okay. How do you convert all of this to 1? Simple. Go to R and then just do find replace. Find and replace. And when you do this find and replace in this Excel, oops, just want to make it smaller. This find and replace, the first box says find what? And then just type Christians, just as it is in the chart, Christians. And then replace it with what? 1. So you type 1. And then you click replace all. You see, you can see that it has replaced everything that is Christian with 1. And then every other thing must be 0. So Muslims, type Muslims here in the chart and then do 0. So every Muslim will replace by 0. And then type Buddhist again. Next thing. So Buddhist, be sure that the spellings match each other. Okay. Buddhists, and then every Buddhist too must be 0. And now you've been able to create a dummy variable for Christian. Now you can do another one for religion Muslim. Okay. But that would mean that you need to bring the things you copied back here. Religion. Bring everything back there. So you just go and copy the information you had for religion. You come back here and then you call it religion Muslim and then change it to RM. And then once again, you go through it and you can use that to decode everything. This is an easy way. Okay. And when you finish, you can delete this. It really help you to be able to come out. So now that we have this thing in coded form, you can now generate your your correlation analysis. Okay, you can do the correlation analysis easily. How do you do that? Okay. Now, the reason why you want to do this correlation analysis is that it's quick, and then it also helps you to be able to get information. All right. So how do you do the correlation analysis? Click on Data tab. Okay. Data tab. And on far right, you use Data Analysis. Okay. The data analysis will come down as a pop-up. And in that pop-up, look for correlation and double-click. Okay. I saw correlation there, double-click. And then in the correlation, delete everything that is here. And then in the input range, just highlight everything that you have. Highlight everything. Once you've highlighted everything, okay, I'm just going back. So once you highlighted everything, they are all collected inside the thing. And then choose labels in first row so that the names will come. And then choose output range where you want your results to be. Click there and just click on the right here to show the results. And just click OK. Okay. Your results are beautifully populated here. The results are having too many decimals. Okay. So you can just go to your home tab. Okay, and just click general. You see the word general. You want to click on the arrow at general, just choose number, and watch the numbers will tend to 2 decimals easily. So this is now your correlation matrix. But remember, this correlation matrix doesn't have what is known as, it does not have p-values, significant values, so that you will know that there's a significant correlation between this. Now, it is this same analysis that you can use for your isotonicity test, okay, which we will talk about later, because your isotonicity test will look at, there must be a positive correlation between a dependent and an independent variable. Okay, but there mustn't be a high correlation between 2 independent variables, because that will lead to multi-collinearity. And in terms of input and output, you want the input to be not highly correlated among each other. But an input and an output must be highly correlated with each other, if in terms of input and output. So you cannot take this thing into your data and then speak about it. That's how you generate correlation in Excel. So your first question is, tell me 2 pairs of variables that are perfectly correlated. Very simple question. Who can tell me that? 2 variables that are perfectly correlated. Anybody? Okay, good. So you have Q, and Q is perfectly correlated. And then C and C is perfectly correlated because they have a correlation value of 1. They are perfectly correlated. Anything that has a correlation value of 1 are perfectly correlated. Now, let's move on. Which 2 pairs of variables are mostly correlated with the response variable? The response variable is Q. That is Q. So let's go and see which variables. So that is why you look at this column here. Which variables are highly correlated with the response variable? The first one is P and Q, which is negative 0.87. The next one is RM and Q, sorry, OTR and Q, which is negative 0.878. And then RM and Q. So those values are highly correlated with the most, with the dependent variable, which is good. It's good because you want a high correlation between the independent variable and the dependent variable. Anything else, okay, among those correlations there, anything else which is not highlighted will be defined, except the, excluding the 1, 1, 1 on the diagonals. Anything else will be defined as multi-collinearity if it is too high. But of course, we need to check that at a later time. So that is how you can do. So if I should ask you that which pairs can be considered to be multi-collinear, okay, which one can be considered to be highly multi-collinear? In fact, we'll come and treat multi-collinearity, but this is just a warm-up. Okay. The independent variables that you see here, the independent variables, the most highly multi-collinear pair, the most highly multi-collinear pair is Dinah.
The OTR and P.
OTR and P. What's the correlation coefficient?
0.76.
Exactly. So 0.76, that is a 1. So if there's supposed to be a multicollinearity issue, those two independent variables. Remember, multicollinearity exists when two independent variables are so highly correlated that it becomes quite difficult to disentangle the partial effect of one from the other on the dependent variable. Okay. And so that is it. But this is just a way to showcase your correlation matrix for the inputs and the output, or for the dependent and independent variables. Okay. You can look at this on your own and then correct them. All right. Now, yes, question. Dana.
Yes, Doc. Please, at which point do we say it's highly? Is it above 50 and 0.5?
Okay.
Or at which
There are
point?
so many guesses on them. We'll treat them later. But then some people suggest 0.7 and above is high, but you can deal with it. So there's a special way of dealing with it. It's by using something we call variance inflation factor. Okay. And some books suggest that when your variance inflation factor is 5 or more, then there's an issue. If it is, then there's an issue you can deal with, you can live with. If it is 10 or more, then there's a bigger issue, you got to deal with it. Not you can deal with it, but you have to deal with it. If the variance inflation factor is 10 or more. So we'll come and use that to correct this. Okay. We'll come and identify and then correct. But it's not, using just the numbers alone is not enough. Looking at the numbers alone, there's no specific cutoff. Okay. All right. Now, how do you do all of this in R? Now, in R, this command, pairs, gin, color it red, it will create the scatter plot matrix of the whole data. So I want us to go to the R and go and do that scatter plot matrix of the entire data set. How do you do the scatter plot matrix of the entire data set? And that is by using the command pairs gen. Pairs gen. I want to just use that here. Sometimes when they are, and it's best at this stage to use the, what do you call it? To use the ones that have been coded. Because if you use the ones that have the dummy variables, uncoded dummy variables in it, it's not going to work. Okay. So it's better to use the ones that have uncoded. I'll give you an example of what I mean by it's better to use the ones that have the dummy variables. So if you look at my pairs command here, gen. Okay. Let me see if I can give you the magnifying glass to look at things better. Okay, so I'm typing gens here, okay, pairs, gen, and then I do my color and I will apply color red to it. I just did that. And it says that unexpected string constant in pair, just as I indicated. Even that I needed to close there. Okay, so that is it. Unexpected information there. Oh, I still needed my equal to, sorry. It might work. Non-numeric argument, that's the one I want to talk about. So because one of the values are non-numeric, and we know location, occupation, religion are non-numeric, it doesn't work. But what you can do is that you can pick the ones that are, non-numeric. So if you are to use the coded data, everything will show nicely. And in order for that to show, I just want to go to this section and just detach and then attach. Okay, so I'm going to detach and then attach the coded one there for you, because I want us to use the coded one for this purpose. Okay, I just want us to use the coded one, just to demonstrate that when you use a coded one, it's better. Okay. Of course, there are advantages in everything and there are disadvantages in everything. Okay. There are always advantages and disadvantages in everything. So I just copy this data again. I go to my and then I reload this data just with the coded. That's the whole idea. Okay. I reload the data just with the coded. Let me just show you how it looks down there. This is how it looks down there with the coded. And at this stage, with the coded, I can just do my pairs. And this is the result up here. So I do my pairs, and you can see that the variables are all showing the results. This is a scatter plot matrix of information that you are looking for. That's a scatter plot matrix of the information that you are looking for. So that was a command here. Okay. And then you can use this pairs to also do scatter plot matrix of some of the variables, not all, some. So you can see that here I did location, religion, I didn't bring a copy. Then you can use CoreGen to do the Pearson's correlation, the one we did in Excel. Okay. So let's do that. CoreGen, and then we see what's going on. So this is our CoreGen command. Okay. I run that. Now look at the bottom here. And you can see that this is what you get for the correlation matrix. The slight issue is that this one, the numbers, the decimals are plenty, and then the off-diagonal elements are also not the. So this one doesn't look that much beautiful like the one in the Excel. And again, the decimal, that's for the decimals, you can change them. You can change the decimals. And how can you change the decimals? It's a very, very simple thing. The only way you can change the decimals is by using round. And you now specify. So let me show you that. How do you use round, call, and then specify? If you come somewhere down here, okay, I just want to just pick on one of them. Just pick on one of them. Just do let me just take this. So you just type, watch how I type round into bracket, and once you do into bracket, you type bracket and then you type your gen, the name of the data set. And then you now close the bracket and then write the decimals. So step out of that bracket and then use the decimals. Bring the comma, use the decimal, write 2, like what I've just done here. Okay, let me give some bit of instruction for this. Okay. So this is correlation matrix that you want to do. Correct to 2 decimal points. So that is it. So you run it and look down here. When you look down, you see that everything is now in 2 decimals. Of course, it doesn't remove the off diagonal. You can do 3 decimals, okay, by just changing the number 2 to 3. And you will have 3 decimals of correlations all here. Okay, but I think 2 decimals is beautiful. And then you can now showcase that. Now, the other thing is that, the other thing is that you can decide, and all of these things I'm teaching you because it's very important for you to appreciate and use them. Okay? You can get p-values for the correlations. you can get p-values for the correlation. Because sometimes correlation is 0.8. Is this significant or is not significant? To get the p-values, install this command called H miscellaneous. So you have to install and then load this command. I'm going to just load it because I've installed it already. Once you loaded that command, you can do correlation with p-values. And that's a very simple thing you can do. Okay? The way to do it is just type. Let me just type that there. Okay? You type this R call into bracket as.matrix. So, and you are using this on the numeric. You do that. Watch down here. You get the information in 2 decimals, and then you have a correlation p-value for every one of them. So as an example, the correlation between Q, okay, let me just give you an example. The correlation between P and Q is negative 0.87, negative 0.787. So you come down here, P and Q, and watch it. You see that that correlation is significantly negative. So that's a p-value at the bottom. The p-value will tell you that a correlation is significantly negative. So that's a very, very good thing that you want to be able to appreciate, because once you have the, but you're not going to put this in Excel. So you will now have to now put star, star, star here, okay? Because this is significant at 0%, okay? And so you have to put 3 stars, because 3 stars is the maximum significance, you might say, okay? Or 4 stars. And then you check, not all of them have significance. For example, the relationship between OT and Q is 0.49, almost 50%. 50% is way above 5%, so it's not significant at all. Okay. So that one will not have a star. So in your correlation, you can put star star to indicate significance of them all. And once you are done with that, you can now say that there is a beautiful situation. Ladies and gentlemen, that brings us to the end of this example of using this data for one, descriptive analysis for the whole data, descriptive analysis for groups of the data. Then we've also looked at how you can actually analyze this for, correlation. Correlation that show no p-value, both in Excel. And then how you do the correlations, this time with p-value to indicate significance. Okay. So as an example, I just want to show you something very quickly before I wrap up. As an example, you can take this information here. If you did this thing in R, you can take the information here and just go to your Excel. I just want to take any Excel. This is an Excel I'm on here. And then paste that information right here. But when you paste, you have to convert it. You have to convert it. So how do you convert it? Okay. And if you want to convert this, I hope you can see the Excel. Okay. You go to data. Under data, you go to text to columns. Okay. Text to columns and select delimited. If you look down here, you can see that it has even started arranging them for you. You click next. Okay. You click next and you can keep it at tab. Okay, tab. And just click next and just click finish. Oh, let me just do it again. Okay. Let me just quickly do this again. Oops. Okay, so you go to data, and then you choose your delimited, choose your space. That's where you use space and click finish. So you can see that it has now beautifully been able to put all of this into Excel, and then you can now remove the information you wanted to remove. all of these things that are, you want them to showcase, you don't want them to show in the, you want to remove all the off diagonals. Okay, if you want to remove all the off diagonals, just start removing them. And they start looking nice. That's it. Normally, you want the thing to be looking nice. So you can use your computation so that it just looks like the one in Excel. Or you can use the Excel one. The reason why we have to pick the one from R is because we want to put the stars there. And then down here, you can just add your triple star. Okay. You want to add your triple star to date. Or you can export it to Word and then do it there. Because you are doing it in R, it's not allowing you to put a triple star. You can export it to Word and then just put a star all over there. Okay. So that is how you can put it into your thesis and beautifully talk about it in a very nice fashion. So that ends our lecture for today on correlation. Next time we shall do a simple regression and a multiple regression and then solve the issue before we now understand how the regression is working. And then we can now conclude with it.